Hello and welcome to this deep tech interview with Samtec for Mauser. I'm your host Stuart Cording, the electronics reporter. Now, as an embedded systems developer, I'll be honest and say my primary focus has always been on the microcontroller, its software, and getting the thing to work in the application. And I come from an era where the highest frequency signal on the board was typically the quartz for the microcontroller's clock. So when it came to connector selection, the basic thinking was, how hard can it be? However, progress marches on, and today's single-board computers are kitted out with interfaces like USB, Ethernet and PCIe interfaces with signals at hundreds of megahertz and more. And wherever you are on the technology curve today, your next project will probably use signalling that is 10 times faster. Someone who guides customers through the host of extra challenges that arise as this happens is Matt Burns, Director of Technical Marketing at Samtec, and he joins me now. Hi Matt, and thanks for joining me.
Stuart, that was a great introduction. I'm glad to be here and look forward to our conversation.
Right, let's get started then, because I've got a whole list of questions for you, because I've been doing a little bit of reading before our chat, and I realised that there's a lot more to connectors than I'd ever taken time to consider. So I thought it'd be a good idea to base our discussion on a trend in the embedded market at the moment, the advancement in platforms like COM Express and COM-HPC. Maybe you could start by telling us a little bit about these two standards, especially the interface technologies they use and the signaling frequencies that are involved.
That's a great place to start when it comes to signal integrity in the embedded world, Stuart. Most of your listeners, if they're in the embedded space, are going to be aware of a COM Express module. COM Express technology obviously has been championed by PICMIG. I like to call it the workhorse of embedded computing because of the fact that it's been around for 15, 20 years. The spec and the boards have adapted to what you referred to as in the increasing speed, increasing performance of microprocessors. COM-HPC. If you were in embedded world recently here a few weeks ago in Nuremberg, new solutions coming out. It seems like from new suppliers every year. So even though at the legacy form factor, it's been around and continues to find homes in a number of embedded computing applications. The challenge with COM Express is the fact that the original form factor, while backwards compatible, across multiple generations, across multiple product selections, some of the first CPUs that came out using COM-HPC back in the early 2000s are obviously obsolete at this point in time. It's kept speed with the advances in silicon to a degree. So the latest specification for COM Express, it was version 3.1, leverages the existing infrastructure to get up to support PCI Express 4.0 or data rates up to 16 gigabit. That's fast enough for a number of applications, but the performance of COM Express is limited by the interconnect. And that makes sense because the interconnect chosen for COM Express when it first came out 15 years ago was bleeding edge, cutting edge, but there's only so much signal you can fit through a certain connector for so long. So to support next gen connectivity, we're starting to see embedded computing processing platforms, CPUs, GPUs, FPGAs with PCI Express 5.0, 32 gig transfers per second. Native on the solution. Very soon, in the next year or two, we'll probably see PCI 6.0, which gets you up to 64 gigabit per second. So there's, PICMIG realized that there was a migration path needed to support these data rates. In addition to PCI 6, you have to support making that jump from USB 3 to USB 4, making that jump from a gigabit Ethernet to 10 gigabit Ethernet or 100 gigabit Ethernet with 4x25. G performance. So, as you mentioned, FPGAs, CPUs, GPUs, they're getting faster, higher performance. The interconnect has to either be in advance of that or keep up with it. And, that migration from COM Express to COM-HPC is just one talking point that illustrates, what you brought up in the introduction of our conversation.
Now, I imagine sort of like in any system like this, one of the key points then when it comes to that the connector from one board to another and the connector choice is that the designer wants to make sure the received signals match the transmitted signal as accurately as possible. That's the goal, isn't it? That the signal integrity, or SI, it needs to be maintained. What are the key elements of signal integrity that they're going to be looking at?
How much time we have?
We've got a few minutes, and we can maybe dig in deeper into individual ones.
Yeah, no, I say that to joke, but you illustrate the point very nicely. Signal integrity is really an entire specialization within the area of electrical engineering that focuses on trying to minimize the effects of loss, multiple types of losses across the signal channel. And think about let's go back to a COM-E or a COM-HPC ecosystem, right? If I'm trying to get a high-speed transceiver or high-speed SerDes out of the transceiver on the core silicon, CPU, FPGA, I don't really care what the silicon is. That signal may have to go from the die to the package to the PCB through a via, back up through a top layer or signal layer trace, either to the mezzanine connector down to the carrier card and out to a I/O connector on the carrier card, or some, it may be a DDR trace that goes to memory on the SOM. So signal integrity specialists, when you're looking at PCI Gen 5, PCI Gen 6, DDR5, DDR6, 100 gigabit Ethernet, the special signal integrity specialists are tasked with making sure that the entire signal channel, from point A to point B, where the entire signal routes, is as clean as possible. And throughout our discussion, we'll talk about some of the design challenges that signal integrity engineers face, some of the design challenges that electrical engineers face. System architects, really when architecting a system, have to consider the signal integrity effect as speeds in these high-speed protocols get faster and faster.
So, like you say, there's a lot of different aspects to that, and I know that Samtec has provided quite a lot of background information on all aspects of signal integrity. I was going through one of the white papers that sort of provides an excellent introduction to that, and a few of those sort of key points that came out of that, things to sort of terms that you need to concern out yourselves with are things like insertion loss, return loss, crosstalk, EMI, and things like that. Do you want to take us through maybe your sort of top 5 that you think are, for this particular domain, most important to look at, and what needs to be considered as you're designing?
Yeah, that's a good question, and we could spend hours on this topic alone, but we'll try to do it in a few minutes. So one of the things that we've noticed is that when we're dealing with larger mid-size OEMs, large-size OEMs, they typically have an SI engineer or maybe a signal integrity department. But when dealing with a lot of smaller OEMs, mom and pop, whatever you want to call them, there's typically not a signal integrity engineer on board. So a lot of the partners, a lot of customers that we work with come to Samtec, and we find that a lot of our work designing in next generation connectors is signal integrity education. So this question kind of ties into the work that we do on a daily basis quite nicely. When we look at signal integrity, let's focus on the frequency domain for just a second. There's typically 3 or 4, as you mentioned, 3 or 4 parameters that we like to focus in on at the channel level and also at the connector level to see how solutions are going to work. Insertion loss is the most basic. In an ideal world, signal transmitting from point A to point B has no loss. However, both at the channel level and at the connector level, insertion loss refers to attenuation across the channel. So depending upon the channel you're looking at, the ideal insertion losses may be a few dB. It may be in a PCI 6 signal to signal or SerDes to SerDes application, it may be 36 dB of insertion loss. Return loss is another key parameter in the frequency domain, and all that refers to is energy that's injected into the system and it's reflected back to the user. So we like to think that there's ideal channels within the systems that we design, but that's just not reality. So if a signal goes from the die to the package, there's going to be to the PCB, there's going to be some finite reflection back into the system because of discontinuities. And each discontinuity in the channel will create a return loss. Typically, we look at return loss over an entire system. For digital, we like to see less than, around 10 dB for RF, greater than 15 dB of return loss. Crosstalk just refers to the fact that you have a source signal that's transmitting either, or being received, and next to it, if you don't have proper grounding, some of the noise or some of that signal will be coupled over to an adjacent transceiver pair. You'll see crosstalk both on the near end, that's at the transmitter source. Some of that energy gets induced onto an accompanying receiver, or the same effect on the far end. So those are probably the four key parameters that we look at, Stuart: insertion loss, return loss, crosstalk, both at the near end and the far end. And then you get into more traditional RF areas. You may start to look at VisWAR, voltage standard wave ratio. There's literally dozens of parameters: TDR, time domain reflectometry, which gets to the time domain. But there's a number of parameters that we look at that not only tell us how the channel itself operates, but also how our connector operates within that channel.
Well, that's great, Matt, and you've just touched on the next point I wanted to come to, because I think it's easy to think that signal integrity has a lot to do with the frequency domain, obviously the amplitude of the signal. How much of it am I losing along the way? How much is it being corrupted along that journey from the chip to the connector, then through the connector to the device it's supposed to be talking to? But there is also the time domain to consider. What sort of things am I looking at with regard to signal integrity in the time domain?
Yeah, that's a great transition, great question, Stuart. I think one of the most important time domain specs that we look at is the signal. When the signal is actually added to the channel, is the rise time or the fall time, because the rise time of the signal tells us what the bandwidth that the data signal needs are. So obviously, the higher, the faster the rise time, the more bandwidth you need to make sure that the more bandwidth you need in that channel to make sure that the signal can propagate with minimal loss. So that's one of the key rules of thumb that our SI engineers will look at, is the rise time of the signal, and will it work with the SI parameters of the channel or of the interconnect. Something else we also look at is skew. In terms of skew refers to time domain variances in a differential pair when trace lengths are not equal. Typically, you'd worry about that in a parallel data bus, especially on a DDR. Going from your CPU to a DDR, you want to make sure that all those trace lengths are of equal length, so that you don't induce skew. You're always going to have some inherent skew within a system. Modern SerDes can overcome that, but if you get too much, obviously that can create jitter and the like. Another area where we focus in on skew is especially when you start to route signals over twin-ax cable. In most embedded systems, mezzanine-style connectors or I/O connectors on the PCB are the transmission medium, but eventually there's going to be cable somewhere. And when you're designing high-speed twin-ax cables, our current generation solutions, 112 gigabit, we have about 3.5 picoseconds of skew. Next generation systems for data center speeds at 224, we've got skew down to 1.75 picoseconds per pair. So, without going into a rabbit hole on that topic, those are just a few of the parameters that we focus in on in the time domain when it comes to optimizing SI.
And that's a great pathway into the next question, because I wanted to ask you how Samtec goes about designing connectors in order to sort of make sure you deliver the best possible SI performance for all of the different parameters that are important. And I also wanted to know, for example, with our example that we're talking about with COM Express, COM-HPC, do they also define, for example, all the pin mapping and how the pins are supposed to be used? And does that then, for you as a connector supplier, limit what you can actually achieve?
Well, we'd like to have ideal connectors all the time where we have infinite data rate and zero insertion loss, but those are mathematically impossible. Uh, sorry. So the challenge for us, I like to think I'm funny, Stuart, but I'm really not. I'm an engineer and in marketeer's clothing, but I do the best I can. I appreciate your humor. Jokes aside, there's a lot of technical aspects that go into interconnect design, and it really starts with application. When talking about COM-HPC, COM Express, that's traditional SOM on a carrier, and it's a mezzanine connector. And Samtec's been making mezzanine connectors for 50 years, or almost 50 years. The challenge is we didn't start making high speed until the late 90s, early 2000s. And now that we're talking about gigabit per second speed, 112 gigabit per second in embedded solutions, the challenge there of optimizing SI versus designing something that's rugged for a power or an external application, there's challenges there. So, some of the things that we look at is, what's the pitch between the pins? What's the mating? What's the length of the mating between the contacts? From the terminal to the socket. How much spacing do we put between, not only on the pitch, but also between the rows of the contacts? A good example, just to compare COM Express to COM-HPC. COM Express uses a 220 pin connector, two of them to give you 440 pins. COM-HPC uses two 400 pin connectors, up to 800 pins. And some of the design elements that we put into the COM-HPC connector, not only us, but the multiple providers of COM-HPC connectors that put into them were 0.635 millimeter pitch, 4x100 configuration. We actually spaced out the rows between the pins along the axis of the connector to allow for differential pairs to be routed between the pins. So that enabled, that enables additional ground vias, that allows for better grounding, better isolation to help us to get the performance that we're looking. So, those are just some of the aspects that we look at in designing next generation, what we call open pin field arrays. And the open pin, the contact design is very flexible. It allows that pin to be high-speed differential, a high-speed single-ended signal, power, RF, analog. That's advantageous when you're designing a next-generation SOM standard like COM-HPC. So, not only do we try to optimize the contact design to give the performance that you want, but then, like you said, the pin mapping comes in. If I want to put 112 gigabit per second differential pair next to another, they need to be properly grounded. So a good example of a pin mapping is we'll have, for differential pair, obviously have the plus and the minus, and then for the other differential, the plus and the minus. If you put just one ground signal between the two of them at 112 gigabits, probably not going to work. So we recommend in general 2 ground pins. You have signal, signal, ground, ground, signal, signal. That type of pin mapping, signal integrity influenced design thought, influenced the pin mapping both on COM Express and more recently on COM-HPC. So again, I asked earlier, how much time do we have? we could spend hours just on this one topic, but just with a few of those tidbits, I think it illustrates for you and the listeners, Stuart, the import that goes into, or the engineering analysis that goes into not only the interconnect design itself, but also the pin mapping, the breakout region, et cetera, to get the performance that's necessary.
It's fascinating to hear you describe all of that, because as I said at the beginning, as a young engineer, you just sort of selected the same connector the previous guy had selected, and we soldered that onto the board. And to sort of understand today how much effort and how much thought needs to go into that design for these high-speed interfaces is absolutely fascinating. And one of the other things that occurs to me as we're talking about this is that I guess where the PCB traces meet the connector and the ground plane, that's also impacting signal integrity as well, and that's something that you can't really do much about. So how do you sort of make sure people on sort of designing the boards appropriately?
That's a great question, and that's become a de facto design support value add that not only Samtec but the interconnect industry as a whole provides. Whether you call that a breakout region, which is what Samtec typically calls it for a digital connector like COM-HPC, or a launch optimization, is what you call it for a precision RF solution. It all talks about how it's all referencing the same concept of how do I get that signal from my pin through the solder or the BGA that's attaching the contact to the PCB, taking that PCB from the contact to a via, routing it through a PCB, whether that's on a top layer, a bottom layer, or a central layer, and then how do I build the necessary ground fence around it using vias or power and ground pores on various layers within the PCB. So that kind of verbally illustrates a breakout region concept for one pin. Now, for COM-HPC, multiply that for 800, by
Exactly.
800 for two pins. So there's two ways of looking at this. We provide a general recommended breakout for all of our high-speed connectors, and customers typically, I shouldn't say customers, OEMs will implement that to the best of their ability based on their specific application. To support that, also, our signal integrity engineers offer bespoke support, application-specific support, to optimize the breakout region to get the performance that's necessary. And more often than not, when looking at high-speed applications like COM-HPC, that SI support that Samtec offers, from to a tier 1 OEM down to a startup, is really the differential to get the performance that's needed. So again, Samtec's the connector supplier. We're also providing the SI support to make sure that whether it's a standards application like COM-HPC, COM Express, or something that's more application specific or OEM specific, it's necessary to provide those BORs, those breakout regions, or those launch optimizations for RF connectors to get the performance that's needed.
What I love about my job is the opportunities that I get in talking to experts like yourself. And as you describe and explain it, I sit there thinking, wouldn't it be fascinating to get more into this, to become more hands-on? Do you offer any sort of evaluation boards or testing platforms? And if so, what sort of test equipment do I need to sort of try that out and learn more about signal integrity?
Great question. So yes, the short answer is yes. For our typical high-speed next-generation interconnect solution, there's a number of tools that we offer to help a signal integrity engineer, an electrical engineer, a system architect to verify the performance of the solution. And that could be the time domain, the frequency domain, RF, whatever. So we have a growing suite of signal integrity evaluation platforms. Not only do we provide the kit, or we can provide the kit to our customers and our partners and OEMs, but we also provide how we use that kit to characterize our interconnect. So here's the kit, here's the test report, here's the correlation between the simulation data and the measured data, here's how we tested it, this is the test equipment that we use, whether it's a VNA, an oscilloscope, a TDR, depending upon the specification that they're looking at. And here's an entire SI test report that our SI engineers, our lab technicians have spent weeks or months creating to enable the OEMs to use the interconnect solutions that's needed. So, and when you look, I don't want to talk about any one specific kit, Stuart, but when you look across Samtec's portfolio, we've got these SI evaluation platforms for our board-to-board connectors, our high-speed backplane connectors. More and more, we've got high-speed cabling, from the near chip out to front panel, near chip out to backplane. We've got front panel cable assemblies that we're looking at. We really didn't talk about the optical domain, but we have evaluation platforms for our optical transceivers that customers use to test the performance there in the optical domain. And again, we back that up with all the technical support, the documentation, our field applications engineers, our application engineers at the factory, to enable or try to simplify the design-in process of the interconnect as quickly and as simply as possible.
Now, the other area of sort of development in our environment is simulation. There's ever increasing performance in simulation tools. Is that also something that you offer to sort of simulate signal integrity of these connectors and how they interact with everything else on a circuit board?
Without question, yes. that is becoming more and more essential into the work that Samtec offers. And it kind of affects two areas of the process. We use 3D solver solutions to look at our interconnect in a simulation environment when we're designing it, reiterating it as a digital twin. Look at it from a thermal standpoint. Look at it from an SI standpoint. Look at it from a power standpoint, RF, et cetera, et cetera. So we use bleeding edge simulation tools from ANSYS and some of our other partners to really help us to try to design out all the technical challenges while we're developing the solution. But after we've created it, after we've prototyped it, after we've tested it, we're also using those simulation tools not only at the connector itself, but the entire signal channel at the application. We recently went through some more. I'll just use COM-HPC as an example. We recently went through a work process within PICMIG, COM-HPC. We're working on the next generation of the spec 1.3 that says here's all the SI work we did on the connector at PCI 5. We have to do the same SI work on the connector at PCI 6. So using the simulation tools, using lab measurements, using BER data, whatever the case may be. We did all that work, and it will soon be a part of the next generation COM-HPC specification. One other thing I'll also mention, and this is becoming more and more popular with customers, is we see OEMs using the same tools. So they're using 3D solvers to create virtual twin or digital twins of their entire signal channel from silicon to silicon. So they can get the 3D solver models of the silicon solutions from the silicon providers, and they're asking us to do the same. So we have a growing library of encoded 3D solver models of our interconnects, 56G, 112G, 224G, that we provide to our customers. They can literally just drop that into their channel, simulate away before they actually build anything. So again, this is another one of those topics, Stuart, where we could spend hours talking about. But the short answer is yes. Samtec's using the latest simulation tools from various providers, not only in the design of our interconnect, but also in the application support, technical support of our customer, partner, and market applications.
Well, it's great to hear that that support is there in the simulation environment as well, and the reasons it's there and how it helps even with the development of new standards and new connectors for those standards. As we sort of already mentioned, there's so many different challenges, and those challenges obviously vary as well depending on the type of application you're building, and coming back to that 10 times increase in frequency and throughput for a board. If someone is having that challenge at the minute and they need some hands-on support to get through the signal integrity issues, how do you help people to select the right connector? And if they've already got issues with a connector they've selected, how can they get in touch with you, and how do you work with them in order to resolve those issues? What's that process?
No, that's a great question. And, there's a variety of answers to that, because it really depends upon a lot of things, but it depends also where's the OEM in their SI journey, I guess is the best way to say it. So a lot of SI engineers want to, especially younger engineers, they want to do everything on the web. So, we try to provide the tools that we can on the web to enable self-support to hopefully move past. Maybe that's providing a model. I talked about the 3D solver models, but customers are always asking us for, I need a schematic symbol, I need a PCB footprint, I need a PCB library of all your interconnect. So all that's available on our website at samtec.com. The 3D solver models are, with ANSYS and Cadence and some of the other leading solution providers are available by request from our website. We have our field applications engineers, factory trained, dozens of field application engineers in the major three regions of the world: North America, EMEA, APAC. We have our applications engineers at the factory in various locations around the world. We have a growing team of signal integrity applications engineers that are purely focused on supporting customers via email, call, whatever, for application-specific SI support. And again, that's available whether it's a small startup all the way up to a tier one customer. So, there's a number of resources that we offer to enable OEMs along their SI journey. The best resource for that is looking at our website, samtec.com/SIG, Signal Integrity Group, or you can our team of SI engineers are accessible via email, sig@samtec.com, sig@samtec.com, and they can, the more detail you give, the more support we can provide and help customize the support as needed. In general, Stuart, we're supporting 200 to 250 requests a month along these lines globally. So that sudden service that Samtec has from a technical support, from design support standpoint, really sets us apart from our competition, and it opens doors for us to building successful relationships with our partners and our customers.
Well, that's great, Matt, to get those answers to those questions that I prepared in advance for our session today. Now, one of the things we've been doing with these series of videos is also going out to the community and asking them what their questions would be. And I'm just going to take a look at some of the points we made. Now, one of the things we did was a little survey just to ask people what they felt were the most challenging SI topics they have in both the frequency and time domain. And the one in the frequency domain that was highlighted as being the one that they felt was the most challenging was crosstalk, and in the time domain it was rise time and dispersion. Does that reflect what you see on a day-to-day basis with your customers as well?
At a high level, yes, and those are very specific questions, and I'm always intrigued talking about SI, Stuart, because you can go super deep or super high level all at the same time. Yes, crosstalk is let me just talk about crosstalk for a moment. Crosstalk is a huge challenge, and a good example of that. I'll just go back to COM-HPC. The original design that Samtec had for the COM-HPC connector, frankly, didn't have good crosstalk, and that manifested itself because of the fact that the pins were too close, not only in the X direction but in the Y direction as well. We optimized the BOR. We used the best substrates. We simulated with the best PCB substrates that we could find. We just couldn't get the crosstalk where it needed to be to support PCI 5, and then obviously to future-proof it for PCI 6, because that was the baseline for the interconnect design. So one of the adjustments that we made in the virtual world was actually to, I mentioned earlier, expand the space between the rows of the pins on the interconnect to allow for differential pairs to route not only north and south on the PCB, but also east and west between the various rows. And by adding that additional spacing, that allowed us to improve the crosstalk performance, both near end and far end, to enable the connector to meet the performance specs that were proposed by PICMIG, COM-HPC technical working group at that time.
Now, Matt, one of the other big challenges for engineers out there is on resolving these signal integrity issues and just getting some basic background information. And one person here has written that they'd like any guidance to any sort of websites or other resources that Samtec might have. What could you suggest there?
No, that's a great question, and I appreciate the feedback from your listener. Samtec has created a signal integrity handbook. It's a 32-page brochure. I think it's 32 pages. Haven't looked at it recently. But that signal integrity handbook is really designed to succinctly and quickly be a reference for engineers of any type to understand SI 101. A lot of the information we talked about, the definition of insertion loss, definition of return loss, the effect that rise time has on bandwidth limitation. That and a number of other SI parameters are defined in this brochure. We've co-branded it with Mauser, and it's available directly on the Mauser website.
And that also brings me on to another question that sort of came out through the community as well, because obviously, as you've mentioned previously in the discussion we've had, there's standards bodies that are responsible for all types of technologies, even USB connectors and things like that. Do they actively search you out to help define the standards for the connectors for these modular systems, or is this where you have to sort of reach out to them? And how does that relationship work?
No, that's a great question. And it really depends on the standards body. Samtec is a member of several key standards bodies within the ecosystem that we talked about: PICMIG, SCET, PCI-SIG, CXL, others. When a new standard is proposed, there's usually a information sent out both to the standard body's members and sometimes to the general public. And depending upon which standards body it is, that helps to determine how someone can get involved. Obviously, in a general sense, standard bodies are members driven. So if there's an OEM out there that's listening that wants to get involved in COM-HPC, that requires PICMIG membership. If an OEM wants to be involved with defining the next generation of PCIe technology, whatever that may be, that's handled by PCI-SIG. Next generation SOM standards for embedded applications, that's SCET. They're different. They each have their areas of specialization, but they also are collaborative, and the technology from one is shared by the other. PCI Express goes everywhere. So, you see that in SCET, you see that in PICMIG, you see that in the consumer world. But a lot of the work that's being done within these various standards bodies is SI. So while the main interface into the standards body may not be a technical engineer, the SI engineering resources from the member companies are contributing to these specifications, as we've illustrated throughout our conversation. Just talking about Samtec's experience with COM-HPC, there's no way we could have had the influence that we had on COM-HPC without the contributions from our signal integrity experts. They were essential, not only in the design phase of a new interconnect that COM-HPC defined, but also in the SI analysis that's captured within the work that the technical working groups are doing.
Well, thanks, Matt, for all of those insights. It's absolutely fascinating to understand and see how the work goes on in the background to make sure, the connectors that we have available to choose meet those standards and have really considered all those aspects, especially from SI, right from the get-go.
Yeah, there's a lot to it. I've been at Samtec 10 years, Stuart, in my career. Like you, when I was an engineer 2 decades ago, I'm starting to age myself. It is what it is. Picking a DB9 or a USB connector wasn't too difficult. Picking a 0.1 inch, 2.54 millimeter header, pretty standard. But today it's bleeding edge. Supporting PCI 6 on an embedded SOM, a lot more engineering that goes into it than it used to.
Super. Thanks ever so much.
Thank you.
Well, that's all we have time for, so let's review what we've discussed. Modular platforms like COM Express and COM-HPC make it easier for development teams to match compute to their application needs, but the interfaces each new generation of these standard offers typically provides a 10 times improvement in throughput, and that means the signal frequencies you're dealing with are 10 times higher. This causes a range of challenges in both the frequency and time domain, particularly when it comes to connector selection. Electromagnetic interference is probably the first thing that comes to mind, but there is also insertion loss, crosstalk, propagation delay, and skew as well. Where not already defined by a standard, pin assignment, contact spacing, and even the PCB design can all result in a connector performing below its specified capability. That's why it makes sense to get guidance and support from connector experts and prepare for these issues before they occur. My thanks go to Matt Burns of Samtec for sharing his technical insights on signal integrity and connector selection. If you'd like to learn more about the connectors suited to these types of applications, follow the link to the Mouser website.